Yesterday we were talking about solution of a linear congruence. In fact, we came to know that if there is an equation of the form Ax is congruent to B modulo n, and it has some solution, and how many numbers uh, they are, and what are they? And these three questions were answered in the last class. But the last class was concerned about the solution of only one equation like this. But it is natural then to ask that what would be the solution of if there are many equations like A I x congruent to B I modulo N I. Okay. So for some fixed number of I, that is I equals to, suppose for example, there are n numbers of equations. Okay. So by a solution of this equation, we shall mean a common solution to all these n equations. Okay. That is the same should satisfy for I equals to 1, for I equals to 2, for I equals to 3, and so on. So that common solution we wanted here. Okay. So something which is a very some requirement or some supposition which was for this is going to be also taken for this kind of equation. And to solve this equation, we assumed that if the greatest common divisor, okay, if the greatest common divisor of A and N is D, that is the greatest common divisor of A and N is D, then there would be D mutually incongruent solution. Okay. So this was the assumption. One more thing is that if A and N are relatively prime, then what we can say that is if D is equals to 1 in this case, then there will be only one solution. And in that case, we can say that this is a unique solution. Okay. In that case, we can say that the equation has unique solution. Okay. So let us take a corollary to that result, what we have discussed yesterday, and then we can move towards some example, at least one or two examples. Let us see. I think one example we did yesterday. Okay, so we can have some corollary, and then we can take up the Chinese remainder theorem. So corollary is that corollary to that theorem is that if greatest common divisor of A and N is 1, that is they are relatively prime, then the congruence Ax congruent to B modulo N has a unique solution. Okay, as unique solution. Fine. And one more thing we can take it out from here, the second corollary. And it says that for given prime integers A and N, given primes A and N, the congruence Ax congruent to 1 modulo n. Okay, Ax congruent to 1 modulo n has a unique solution and this solution is you know that when A is given and we want to find x such that their product is congruent to 1 modulo n. So it means that we are searching for inverse of A. Okay. So this solution sometimes called the multiplicative inverse modulo n. The multiplicative inverse modulo n. So these were two important corollaries to the theorem we discussed yesterday. All right. Okay. Some examples we took yesterday. In one, let us take one more example, and then we can move towards Chinese remainder theorem. So if we are given to solve 9x equals to congruent to 21 modulo 30. Okay. Now you see that if sometimes if you have you know that in general cancellation law doesn't hold in congruence, but thing is that under certain condition you can cancel it out. Okay. Okay, so here we see that the greatest common divisor of 9 and 21 is what? 3. Okay, 9 and 21 is 3. And okay, 9 and 21 is 3. And here A equals to 9 and B equals to 21 and N equals to 30. Okay, so here value of D is 3. So there are exactly 3 solution of 1. Okay, 3 solutions of 1. One solution we can try it out. What would be the possibility for one solution? We can find out by inspection. So here we find that x equals to x0, and we can take x0 is 9. So 9 times 9 is 81 minus 21, and it is going to give us 60, and 60 is divisible by 30. So x0 equals to 9 is a solution. Of 1. So other solutions are obtained by other solutions are obtained by how we can obtain solution. How can write x equals to x0, and of course you can as yesterday we were using negative sign, so if you wish you can use that, but if you want you can use also the positive sign. So 30 by 3, that is this greatest common divisor. Okay, so times t. So this is equals to x0 is nothing but 9 plus 10 times t, and t can take value 0, 1, 2. Okay, 3 values. So t equals to 0 will give x equals to 9, and t equals to 1 will give x equals to 9 plus 10, 19, and 19 under modulo 30 is nothing but 19 only. Okay, and when t equals to 2, we will get a 20 plus 9, that is x equals to 29. So we need not to reduce them because they are less than 30. And in case if you have taken x0 minus 30 by 3 times t, where t equals to 0, 1, 2. So in that case, you will be getting 9 times t. Okay, where t is 0, 1, and 2. So for t equals to 0, you will be getting x equals to 9, and t equals to 0, t equals to 1, x equals to 9 minus 10, and 9 minus 10 is nothing but negative 1, and negative 1 is equals to or congruent to 29 modulo 30. Okay, and again, if you are taking 2, then you will be getting x equals to minus 20, minus 21, minus 11. Minus 11, 20 minus, minus 20 plus 9. So minus 11, and this minus 11 is congruent to 19 modulo 30. Okay. So finally, we have this solution 9, 29, and 90, the same here. Okay. But the thing is that here we initially get some negative quantity, and then we need to change them to positive quantity. Okay. Under using the operation, respective operation in that equation. Okay, so here in that case, we need to reduce this negative 1 and negative 11 to their respective equivalent number under modulo 30. Okay, so this is how we can solve. So next, let us see if we have so many equations, not only single equation, but we have 3, 4, 5, or 2 equations, and we need to solve them. So how we can solve them? Okay, so in that case, we need to search for a common solution to them or satisfy all the given equations. Okay, so let us see that this is called Chinese Remainder Theorem. This concept was started initially in China. So that's why it is named as Chinese Remainder Theorem, and later on it was developed in Greece. Okay. So they also worked on, but in particular case, it was discussed by some Chinese researchers. Okay. So it says that just a minute. What happened? Okay. So let us see. It says that let n1, n2, n3, and nr be positive integers. Be positive integers such that the greatest common divisor of ni nj is equals to 1 for I is not equals to j. Okay, that is they are mutually co-prime. Okay, so there then the system of linear equation Okay, linear equation or congruences. Okay, AIX is congruent to BI modulo NI, where I equals to 1, 2, 3, and up to R we are taking. Where greatest common divisor of A, I, and Ni equals to 1 for all I has a solution, has a simultaneous solution, in fact, okay. As a simultaneous solution, it means that the same solution will satisfy every equation, that is R equation, all these R equations, has a simultaneous solution. Simultaneous solution, which is unique modulo, to the integer m equals to n1, n2, nr. Okay. Something we need to see here that we are taking from the last theorem is that A, I, and Ni should be relatively prime. Okay, so this is also necessary. There should be relatively prime for all, because if you want simultaneous solution, it means every equation should have solution. So that for that it is necessary AI and Ni should be relatively prime. Okay, and moreover that Ni and J, they have been also assumed as relatively prime. Okay, so these two assumptions, with these two assumptions, so these are linear congruence equations will have a simultaneous solution, and which is unique up to modulo m. It means that if you are taking any solution, then it will be equivalent to some that particular solution what you have obtained. Okay, unique up to modulo m. All right. Just like we wrote here that this minus 11, this is equivalent to 19 modulo 30. So if negative 11 is also satisfying that, you can substitute and you can check. Okay. If you are substituting here, negative 11 here, so 99, and then you will be getting here what? Negative, negative 99 and this is 21. Okay. Negative 99 and 21. So you will be getting 99 and then 100 and then 20, 120, negative 120. You will be getting one, you will be transferring this. Like minus 99 is there from here, 9 times minus 11. Okay. And then minus 21, this is going to give you negative 120, and negative 120 is completely divisible by 30. Okay. So negative 11 is also a solution, but thing is that this is equivalent to 19. Okay. So some other solution also you can get, but thing is that there will be exactly 3 solution in this case. So similarly here you will be getting so many solutions, but they will be equivalent to the solution you have obtained using this method. Okay. So let us proceed for the proof. Okay. So we need to consider the equations AIX is congruent to BI modulo NI. Okay. and I equals to 1, 2, 3 up to R. Fine. So here considering these R equations, and since AI and NI are relatively prime, that is the greatest common divisor of AI and NI equals to 1. So there exists CI such that AICI is congruent to BI modulo NI, and this is a we are able to write with the help of the result we discussed yesterday. Okay, so this was the condition under which this kind of solution AIX congruent to BI modulo NI possesses solution. Okay. So for each I, we have a solution, and that solution is Ci. Okay, that solution is Ci. So now let small mi equals to capital M divided by Ni, where you know that M was given here, the product of small ni's. So this is N1, N2, N3 up to NR. Okay, so this Mi, Mi here, this product, this is the equals to M divided by Ni's. It means that Mi doesn't contain Ni. That is, you know that you can write it Mi equals to N1, N2, N3, and so on, and you here Ni plus 1 is there, Ni minus 1 is there, but Ni is missing because you are dividing it by Ni, and then next Ni plus 2 and so on, NR. Okay, so this Mi doesn't have Ni. Okay, so this means that the greatest common divisor of Mi and Ni, because Ni is not available in Mi, okay, in this product it is not there, so they are going to be relatively prime, and this is true for all I. If you are taking M equals to 1, I equals to 1, 2, 3 up to R, so they are going to be prime. Okay, relatively prime, Mi and Ni. Okay, uh, and of course this is evident. Otherwise, you can say something about this, that this is because uh, for if P uh, P a prime such that P divides the greatest common divisor of Mi and Ni. Okay, then Pi divides Ni, and also P should divide Mi. Okay, fine, and this implies that P divides Ni, and P also divides Mi sort N1, N2, Ni minus 1. This is minus 1, Ni plus 1, NR. Fine. This is NR, and this implies that P divides Ni, and P divides then P divides then N J. Yeah, Nj. Okay. P divides Nj. This implies that yeah, P divides Nj. If P divides the product of these, then P divides some of these Nj, and I is not equals to J. Fine from here. So this implies that P divides that is P that is P. Okay, P divides Ni and Nj. So therefore, the greatest common divisor of Ni and Nj is not equals to 1 when I is not equals to J. And this is a contradiction. Okay. So therefore, the greatest common divisor of Mi and Nj should be 1. That is, they should be relatively prime. Okay. So next, what we have assumed that there is a solution because of a consideration that ai and I are relatively prime. So there should be solution to each equation, and this solution is nothing but Ci. We have assumed. So ai and Ci, ai Ci is congruent to bi modulo Ni, and then we are constructing small mi is equals to m capital M divided by Ni. And then we claim that Mi constructed so and Ni, they are relatively prime for each I. So until now we have done this. Now next, okay. So we have thus the greatest common divisor of Mi and Ni is equals to 1 for all I. This implies that there exist, because they are relatively prime. Okay, so there exists an integer mi bar such that mi bar such that uh, mi and mi is congruent to 1 modulo such that this is congruent to modulo Ni, and this is true for I, all I. Okay. All right. So now consider, you know that we have constructed this Mi is equal to capital M divided by Ni. Okay. And now we are looking for the inverse of this. Okay. And for inverse of this, we just saw something here. Where it has gone. Somewhere, I think, yeah, here. Corollary to that, if A and N are relatively given primes, okay, they are given primes, that, and of course, if they are prime, then they are mutually prime. So the congruence Ax congruent to 1 modulo has a unique solution. Okay. Okay. So here our Mi is there and N is there already. Okay. So we are looking for this X, and this X we assumed that it is Mi bar. Okay. So we are using this thing here. Okay. So Mi bar is the inverse of Mi. Okay. Now consider capital X equals to C1 M1 M1 bar plus C2 M2 n2 bar plus dot 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 plus CR MR bar. Okay, so let us multiply on both sides by AI. So we have here AI C1 M1 bar plus C2 N2 N2 bar plus dot 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 plus CR, sorry, AI. Okay, here AI is there. AI CR MR and MR bar. So you are just pre-multiplying this X, this expression by AI on both sides. Okay. And because we are taking the multiplication modulo Ni, so in each Mi skips Mi skips Ni. So Ni will be there, Ni will be there, Ni will be there. This here is yeah, here is I. Okay, Ni will be there. Okay. So if you divide the each term by multiplication, if you reduce each term with multiplication modulo Ni, so what we will be getting? Except one term, every term will become 0. So we are left with only one term AI, Ci, Mi, and Mi bar. And this is a multiplication modulo Ni. And this is because each term except ith contains Ni. Okay, is it okay? And also now you see that Mi and Mi bar under modulo Ni is nothing but 1. Okay, so we have AI and Ci, AI and Ci, and this becomes 1. So we can write AICI modulo Ni, and this is true for all I. Okay, and then this AI and Ci, if you see here in the starting, this is congruent to Bi modulo Ni, and therefore we can write it Bi modulo Ni. So like this. Okay. So what we have this implies that AI capital X is congruent to Bi modulo Ni, and this is true for all I. So this shows that X, capital X, thus capital X becomes a solution of the given system of equations. Okay. Now thing is that what is left there, this is unique solution. That is what we need to prove. Okay. So X is a common solution. X becomes solution of given system of equation. It means that X is a common solution of the given equation. Okay. Now suppose Y is also another common solution of the given system of equation. And so AI capital X is congruent to, or we can write AI is capital X is congruent to Bi modulo Ni. All right. Okay. So actually, this in fact this uh, this becomes a capital X becomes a common solution, becomes a solution. In fact, a common solution. Let us write. Okay, a common solution. That is, it is solution of each and every equation. Okay, common solution. Okay. So AXI equals to BI, this we have, and because Y is also a solution, so therefore we can write A Y is congruent to BI modulo NI. And these two together implies that AI capital X is congruent to AI is congruent to AIY modulo NI, right? But you know that greatest common divisor of AI and Ni equals to 1. So we can cancel out AI. So we have X congruent to small y modulo Ni. So this means what? That X and Y, capital X and small y, are the same or equivalent under multiplication modulo Ni. Fine. Is it okay? All right. So now, but the thing is that you know that we need to find the unique solution, unique modulo to the integer this, and we are saying that this is a solution under multiplication modulo Ni, not capital M. So let us see how we can say that with the help of this. Okay. So X is congruent to Y modulo Ni, and this implies that Ni divides capital X minus Y. Okay, capital X minus Y, and this is true for all I. Okay. Now since the greatest common divisor of Ni and Nj, that is, they are relatively prime, for I is not equals to J, so there is 1. The greatest common divisor of Ni and Nj is 1. So this means that the greatest common divisor of N1, N2, and up to Nr is going to be 1. All right, because they are mutually prime. And you know, by using the a relation between LCM and greatest common divisor and least common multiple, because the greatest common divisor becomes 1, and therefore the LCM, least common multiple of N1, N2, and NR is going to be N1 times N2 times NR, and this is nothing but M. Okay. And because each Ni divides X minus capital Y, so this implies that this product capital M should also divide X minus small y. Fine. X minus small y. Okay, let me write it another way. That is okay. I think here I have written. Okay, here I have written that Ni divides capital X minus Y for all I, and therefore their least common multiple, that is capital M. This implies that capital X minus Y, M divides capital X minus Y. Okay, and therefore what? Therefore we have X is congruent to small y modulo capital M. So this proves the result. Fine. This proves the result. So I think we don't have much time today. We'll be saying some examples based on this Chinese remainder theorem tomorrow. So for that, for tomorrow, until tomorrow, bye-bye.
Thank you for watching this video. To stay updated, please subscribe to our YouTube channel, Cosmos Learning. Happy learning through Cosmos Learning. To watch more, click on any of these cards. Thank you once again.